Our next piece of 2.4 day 1 is something called the remainder theorem. Now, the remainder theorem is very much related to synthetic division, just like we did last example. And so we're looking for specifically the remainder, and we can find this by long division or synthetic division. But if we've got a divisor here, it looks like we've got x plus 1 as the divisor, then we might as well use synthetic division. So here's what we start with. We find k. K value, since it's x plus 1, k is negative 1. And then, like before, we're going to put the coefficients from the dividend on the inside. So 3, 7, negative 20. All right, so I'm going to go through the process just like I did with normal synthetic division. Bring down the 3, multiply it by negative 1, add those two together, we get 4, and then multiply negative 4 for those, add those together, get negative 24 as my remainder. So that's my remainder of this one. We're going to talk about this remainder theorem, which is an alternate way of determining the remainder here. It's going to give us the exact same thing, just a different way to do it. And so notice what the remainder theorem says. It says if a polynomial f of x, that's this right here, is divided by x minus k, all right, there's the x plus 1, that represents that, then the remainder r is f of k. All right, so let's just kind of remind ourselves what k was in this problem. K was negative 1. So we can take that k value and just plug it into f of x. So we have f of negative 1. Negative 1 was our k. And then we can plug it into this up here and supposedly get the exact same thing. So we do that. 3 times negative 1 squared plus 7 times negative 1 minus 20. All right, so that looks like we've got here negative 1 squared. That's 1 times 3 is 3. 7 times negative 1 is minus 7, and then minus 20. And lo and behold, we do actually get negative 24. So it's just this, be able to find the same thing, be able to find the remainder either way in this case. Now, you might be wondering, why would I want to do that? It seems like this is plenty easy. I could just do synthetic division every time. But I'll give you one example that might, convince you a little bit. Let's say that we wanted to do something like x to the 100 plus 4, and then divide that by, I don't know, x minus 1. Okay. If we're going to do this problem by synthetic division, think about the things that we'd have to do in this table. As I mentioned in the last one, if you start with a higher power like x to the 100, but then a bunch of them are missing, we'd have to have like 98 zeros in between there, and that would make this problem a huge pain to do by synthetic division. If I have it with the remainder theorem, though, all I would have to do is find out, okay, what is k? Now, in this case, k would be equal to 1. So if I wanted to find the remainder from this one, I could just plug in 1 to the 100th plus 4 and get my answer. Well, we know 1 to any power is just 1, so that's just 1 plus 4, and that's 5. So that would be a lot quicker than plugging this into synthetic division and trying to put all those zeros in there. So that's where the remainder theorem can be a bit of a help to you if we're dealing with those types of polynomials.